We're now ready to consider the final property, which is the transitive property. A relation on A is said to be transitive if for all x, y, and z in A, if it is the case that x relates to y and y, which is the second element of the first relation, relates to another element called z, then the transitive property will only be there if it is also the case that x relates to z. In a schematic, we might see that as follows. We might see that if x relates to y, so x is related to y here in this picture, and if it is also the case that y relates to z, that there has to be a shortest path from x to z, meaning that I can get from x to z in 2 steps. X is related to y, y is related to z. For the transitive property to hold, I must also see a relationship between x and z. So in the relation for this picture, what I would see is that x and y are related. And then since y and z are related, what I should be looking for now is there an ordered pair that lists x and z? And if it is the case, then this particular relation that I've just invented has the transitive property. So it's only important that whenever one element relates to a second element, and that second element relates to a third element, we should also see that there's an ordered pair where the first element relates to the third element. So in our first context, where A is the set of elements 1, 2, 3, and 4, we've already listed one possible relation, which is that we're going to pair two elements if they're equal to each other. So 1, 1, 2, 2, 3, 3, and 4, 4 are the only elements in that set. So again, we're only looking for violations of the property. If there are no violations of the property, then the property holds. So in the picture, what I would be looking for is if I see one element related to another element, which I don't see at all, right? There's no two elements that are different that are related in this context because my criteria is I'm only going to relate them if they're equal to each other. So since there is no situation where one element relates to a second element and the second element relates to a third element, I don't even need to worry about the first element relating to the third element. So we have no violation. There is no situation where x relates to y, which means xy is in R, and yz is in R. Since there's no such case that satisfies my premise, then I don't need to worry about the conclusion, because the conclusion only needs to hold. X has to relate to z only if these two conditions are present within our relation. So we would just say there is no violation. Oh, there is no situation where that happens. Then transitive is not violated. So since it's not violated, we would say that R is transitive. That might seem kind of like a weird thing to say, but again, it's like dealing with a driver's license situation. If you drive a car, then you better have your driver's license, but if you don't drive a car, then whether or not you have it is not going to get you in trouble. In our second relation on that same set A, we said that we're going to, in an alternative pairing, we're going to relate two elements if it is the case that x is less than y. So 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, the first element is always smaller than the second. But now I do have to worry about the transitive property. So I see that 1 relates to 2, and I see that 2, for example, relates to 3. And I can see that here. 1 relates to 2, 2 relates to 3, and what I want to check is if 1, 2 is in R and 2, 3 is in R, is it also the case that 1, 3 is in R? Well, it is. It's right here. And so that means that so far so good. And what this really means is that since 1 is less than 2, and since 2 is less than 3, well, that automatically means that if 1 is smaller than 2 and 2 is smaller than 3, 1 is certainly smaller than 3. And this is going to hold for any pairs, right? If A is less than B and B is less than C, then A is certainly less than C. And we can see that on a number line as well, just to prove this for a bigger set. Like if A was the set of all natural numbers, then it would be true for any pairing where if A is here and A is less than B, that means B is somewhere farther along on the number line. And then if B is less than C, that means C is even farther along the number line. That means A is definitely on a lower end of the number line than is C. And so immediately we can say that this is going to be this relation is going to have the transitive property. Also, since 1, 2 is in the set and 2, 4 is in the set, I should also see that 1, 4 is in the set. So since 1 is less than 2, and since 2 is less than 4, that also means that 1 is less than 4. I have, let's see, 1, 3, and I have 3, 4. So we have 1, 3, we have 3, 4. Do we also have 1, 4? We do. We have it right there. So since 1 is less than 3, and since 3 is less than 4, that means I should also see an arrow from 1 to 4. So we can make this kind of general argument. Since if, or I should say, I'll say whenever A is less than B, or AB is in the relation, that means A is less than B, and BC is in the relation, which means that B is less than C. By this picture here, the conclusion is that C is also in that relation because A would certainly be less than C. So R is transitive. In our situation 3, if an element relates to another element, so like 1, 3, and now here's the thing, X, Y, and Z in this transitive property are different elements. X is not Y and Y is not Z. So for example, 1, 1. Well, if 1 relates to 1 and 1 relates to 3, then that does not necessarily mean that 1 has to relate to 3. Well, actually, that element is already in the set. So X, Y, and Z are going to be different elements. So in this situation, we can, just by virtue of the picture, if it were the case that 1 pointed to 3 and 3 pointed to some other value in set A, then I would also need to see that shortcut going from 1 to 2, for instance. But in this picture, we see that an element points to another element, but that other element points to no other element in that set other than back to the first element. So that's where the symmetric property was. But we don't see an element pointing to another element, and then that second element pointing to a third different element. So we have no violation of the transitive property. So I see that 1, 3 is in here. 3, 3 is in here, but then clearly 1, 3 is also in it, right? Because if that was our first pair that we were looking at. 1, 3 is in here, 3, 1 is in here. Well, that doesn't necessarily mean that 1, 1 has to be in there too, because 1 and 1 are the same element. So it's only when the three elements are different, if one points to the other and the other points to a third, then better be the case that the first points to the third. So there's no violation of transitive. There's also no example of transitive, but since there's no violation of it, then that means that R is transitive. In our fourth case, where M is the set of all discrete math students in our class, and we're going to relate two people if person 1 has the same grade as person 2. So let's think about this. Let's suppose, since we don't actually have the set roster, we can't list out all ordered pairs for two reasons. One, there's too many people in the class to pair everybody with everybody else, but also, and more importantly, we can't really share those grades, right? So suppose that there's an element where x relates to y. So xy is an element of that relation, and yz is an element of that relation. So suppose we find such a situation. Well, first of all, can we find such a situation where x relates to y and then y relates to another element? Let's think about this. This would mean right here that x has the same grade as y. Okay, so let's suppose for a second that x, that person has an A, and y, that person must then have an A as well, right? Because x has the same grade as y. Well, in the second statement, we're saying we found another pair, y comma z, and by our context, that would mean that y has the same grade as z. But x has the same grade as y, right? And we already know that y has an A, or at least in our example, we've said that y has an A. And now we're saying we found another pair where y and z is in that relation. So that means y has the same grade as z. So that means that y we already know has an A, and if y has the same grade as z, then z must also have an A in the class. So is it the case that x and xz is in the set? Is xz in our relation? Well, if x has an A and y has an A and z has an A, then x and z both have the same grade as well, right? X has an A, z has an A. So since x and y have the same grade and y and z have the same grade, x and z also have the same grade. Now this is where it was important that we're comparing x to y, and then y we're comparing to another element. So the duplicate is that this y and this y are exactly the same. And so this does have the transitive property. And this is going to be true for all x and z. As long as x has the same grade as y and y has the same grade as z, it will always be true that x has the same grade as z. So R is transitive. Or we could say R has the transitive property. In our final context here, where we define P to be the set of all people in the world, and we're going to relate two people if they're siblings of one another, I actually had to go and look up the definition of a sibling just to make sure we have this down. So a sibling is one of two or more individuals having one or both parents in common. A male sibling is a brother and a female sibling is a sister. Non-binary gendered siblings are usually just called siblings, although various alternate neologisms have been proposed. It's a big word. So let's think about this. That means they have to have one or both parents in common. So let's think of an element, another element, where x and y are siblings. Okay, so I have that connection there. Now let's also suppose that y and z are siblings. So what I have is that x and y are siblings, and y and z are siblings. Can I conclude that x and z are siblings as well? Well, the requirement is that a sibling is one of two or more individuals having one or both parents in common. So since x and y have one or more parents in common, and y and z are siblings, so they have to have one or more parent in common, that means that x and z have one or more parent in common. This could be different if we weren't talking siblings, but we were talking about maybe cousins. So if X has the same cousin as Y and Y has the same cousin as, or Y and Z are cousins, this may change. But since we're talking about siblings, we can indeed conclude that that is always going to be true. So we have to consider the fringe cases. Is there a situation where X and Y are siblings? They have at least one parent in common. Y and Z have at least one parent in common. Well, that means X and Z also have one parent in common. So we're going to conclude here that R is transitive. Now, if X was a cousin, X and Y were cousins, and Y and Z were cousins, that wouldn't necessarily mean that X and Z are cousins, because X and Y could be cousins through the father, through the father's side. Y and Z could be cousins through the, I don't know, maybe the mother's side of Y, and they could be separated by a couple of generations, or they could be separated by a couple of families. So in this case, R is definitely transitive.